Hey, Zoom people, can y'all hear me okay?
Yes.
Okay, cool. Oh, shoot. Um, Oop. I do this every time. Okay, on Zoom, you can use this link to sign in, or I'm about to share the screen. You can scan that QR code. And we'll give it a couple minutes. How do you guys feel about this exam? Yes? No? Huh? Okay, that's fair. This is the longest test prep I think I've ever made, so hopefully it's good. I'll just put it there and then give people a couple seconds to get on. Okay. I think turnout was like there was more people for the last test prep, so I feel like overall as like a class,
Your math
this
class,
is a bit better.
Yeah.
it's like, is it hard?
No.
It's not?
Mm-mm. It's just a lot of homework.
Okay. Okay.
Why?
Okay, I'm sending that link again. Go ahead and use it to sign in, and then I'll get started in like a minute. Hey. Hey, Damien, could you put up with your nose, please? Thanks. It's just for a little bit. Okay, cool. I say we just go ahead and get started. I want to do that. Okay. So basically, I did my best to put this like in order of the chapter. So starting with 6, right? Starting with 6 and then ending with molecular orbital theory. Okay, number 1. Of the following, blank has the shortest wavelength. Which of these waves has the shortest wavelength? So remember, not radio, not UV. Okay, so remember, which is safer for us, shorter or longer? Longer. The longer the wavelength, the safer it is. So this is where you'll find things like microwave, things like radio wave, things that we're constantly exposed to. These are safer for us. So out of these, if I'm asking for the shortest, which is the most unsafe, out of these, which is the shortest? We got an answer from online. How about in person? Huh? Not UV. It is going to be X-ray. Because think about it, UV rays we get from the sun, right? We can go out in the sun. You should wear sunscreen, but I'll bet most of us do not daily. We can go out and we're fine. If you spend a lot of time under an X-ray, that's gonna screw you up pretty quick. What has the shortest wavelength overall? It's not listed. Gamma. What's the formula for the speed of light? Eight is equal to? This is C, yes. Wavelength times frequency. What is the unit for wavelength? Someone online and someone in person. Not for wavelength. Hertz is going to be for frequency. So frequency can be measured in hertz or inverse seconds. This is just s to the -1 is just another way of writing 1 over s. Wavelength is going to be in some type of meters. On my exam, this was one of the free response questions. Just write the formula. I'm not saying that's going to be one on yours because I have no idea what she puts on the exams, but that was one on mine. So, what is the frequency of light that has a wavelength of 2.25 times 10 to the -5 meters? So we're going to use that formula, right? And you guys should know by now with atoms, you're always going to write down the formula you use. So we know the speed of light, it's a constant, it's always 2.998 times 10 to the 8th meters per second is equal to, we have the wavelength, that's 2.25 times 10 to the -5 meters. And then we're looking for frequency. So do some math and then tell me what you get. Gosh, why is the math building always so cold? Also, I don't know if I told you guys this or not, but this is going to be your last exam with free response on it. That 4th exam, she does to mimic the final. There's no free response. Okay, who's done some math? So we are going to have 1.33 because of sig figs, right? What about our times 10? 10 to the 13th. Do you see that on your calculator? Okay, cool. And this is inverse seconds. You will not have to worry about when to use inverse seconds and when you use hertz. She'll tell you what she wants. But honestly, you probably won't have to use hertz in math unless she gives you a conversion factor. Okay, of the following transitions in the Bohr hydrogen atom, the blank transition results in the emission of the highest energy photon. So level 1, moving up from level 1 to level 4, moving down from 6 to 3, up from 3 to 6, down from 6 to 1, or up from 1 to 6. Okay, we have an online answer. What about in person? Someone be brave. Take a guess. D. It's D. Because think about it. So let's say you have 1, 2. You have 6 energy levels. That's like in a game. Okay, let's say you're starting at level 1 and then you work your way up to level 6. Well, that takes a lot of energy from you, right? You put a lot of energy into that. Let's say you make it to level 6 and you die and it sends you all the way back to the beginning. You just lost so much energy. You let off energy. Lost energy? That doesn't sound, you lost experience. Let's go with that. That works. Yeah, you lost energy. You're going down. Okay. Another way, if you're a physics person, if you're really into physics, another way to look at it is like potential energy. If you start out with a ball at the first level, at the first floor, and then you move it up to the 6th floor, you've increased its potential energy, right? And if you move it down, you've decreased its lost energy. Okay, write the ground state configuration for Ga, gallium. This means electron configuration. What does ground state mean? Ground state. Not excited, not excitable. Yeah, it just means it's neutral. So yeah. No charge. So it's just where it is on the periodic table, that's what you're writing it as. Oh wow, there's a lot more people here than in the beginning. Hey, if you got here before I sent out this link, make sure you sign in so that the office can do with whatever they do with that information. Someone read me the configuration so I can write it out. What am I going to start with? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Yep. That's the ground state configuration. You can do that as well. She'll ask you, you'll be able to tell by the answer choices. She'll give you either answer choices that look like this, or she'll give you the noble gas configuration. But these are the exact same thing. It just depends on how she puts them in the question. There are some questions, like on free response, she may ask for the full configuration. She wants you to write out the entire thing. The valence shell of element X contains 2 electrons in a 5s subshell. Below that, element X has a partially filled 4d subshell. What type of element is X? Chalcogen, halogen, transition metal, alkali metal, or main group element? Yes. We have an in-person answer. What about online? What do you guys think? Yes, it is a transition metal. Because remember, when we have that periodic table, it's split up into S, D, P, and F groups. When you have a D subshell that's not all the way filled, you're going to end up here in this transition metal area. The ground state configuration for zinc is, and you see what I mean? She'll give it to you like this. That other one, she like wrote them all out, and I didn't feel like doing that. So I didn't make that. I didn't make it multiple choice. Hả?
Cái nãy này là của chú Hành gì nè, với Hành đó ra bữa kêu Hành đi để lại cho chú Hành đó. Cái gì? Cái giấy nhà băng của chú Hành trả bill gì đó.
Okay. It is C. Argon is the noble gas that comes before it, and then you just work your way across up until you reach it. Okay. Which of the following has a noble gas configuration? What does that mean, a noble gas configuration? Yes. When we have those charges, it means that with that charge, it's going to end up with the exact same electron configuration as a noble gas. So with positive charges, are you gaining or losing electrons? So are you going to move right across the periodic table, or are you going to move left? Left. Huh? Oh, it was you. Okay, sorry. It's so hard to tell who's like speaking to me. Okay, we have an online answer. What about in person? It is all of the above. Chlorine, you lose one, you end up at a noble gas. With this one, I don't know what its name is. I think it's titanium. With titanium, you're going to go back 4, you're going to end up a noble gas. Krypton is a noble gas, so of course that has a noble gas configuration. Sodium, you're going to go back 1, you're going to end up at a noble gas. Which of the following is an isoelectronic series? What does that mean? What is isoelectronic? The same. They're going to have the same electron configuration. So these up here in question 8 are isoelectronic with a noble gas. I don't believe it's the same noble gas, but it is a noble gas for each of those. Okay, we have an in-person answer. What about online? E. These are all going to end up with the same configuration as ground state neon. Okay. So we just went through speed of light stuff. We went through electron configuration. So let's jump into quantum now. An electron cannot have the quantum numbers of n equals, l equals, and m sub l equals. Which of these is impossible? Yes, I can. Okay, we have an online answer. What about in person? Yes. Okay, let's walk through this. So, what does the N number tell you? It tells you the energy level. So here we're at energy level 1. What does L tell you? The orbital type. What orbital type is 1? What is it? I feel like I hear it, but you're going to have to say it loud because the air conditioning's. I think I hear P, so that's what I'm going to put. Does 1p exist on the periodic table? No, we go straight from 1s to 2s. No 1p. So this does not exist. Oh, why is it getting so blurry? Oh, what the heck? Okay, the Pauli exclusion principle states that A, all orbitals of a certain energy level and orbital type must be singly filled before being doubly filled. B, an energy level and orbital type must be completely filled before moving to the next energy level and orbital type. Or C, no two electrons can have the exact same quantum numbers. Wow, you guys were quick on that. C, yeah. But if you'll notice, these two are also laws. This is Hund's rule. A is Hund's rule. I don't remember what B is, but I know it's 1. So it's possible that she will give you something that looks like this. You have 1s, 2s, 2p. She'll give you something that goes like this. That's really poorly drawn, but do you see how both those arrows are pointing upwards? That can't exist. That can't happen. That means they're both a positive 1/2. And that means they would have the exact same quantum numbers, which is not possible. Okay. Equals 1 shell contains blank p orbitals, and all other shells contain blank p orbitals. Is it 0 and 3, 6 and 2, 3 and 6, 0 and 6, or 3 and 3? Okay. We have an answer online. What about in person? What do you guys say? A. Because remember, we said up in question number 10, 1p does not exist. So it has to be 0. Just it doesn't exist. The biggest mistake people will make here is choosing D, 0 and 6. That's the biggest mistake people will make because p orbital can hold 6 electrons, right? Remember, each orbital can hold 2, and you put them in pairs. So this thing that I drew here, these are your orbitals. So the number of orbitals is half the number of electrons it can hold because they're paired up. Okay, each D subshell can accommodate a maximum of how many electrons? 3, 5, 2, 10, 6. Right. 10. How many orbitals does the d subshell have? 5. Okay, cool. I was about to try and like scroll down to like move the paper like on the computer. It's just been a day. I haven't even like this is the first time I've left my room. It's been a day. Okay. Write the complete electron configuration of the halogen in the third period. Box in the valence electrons. What is the halogen in the third period? Argon or krypton? What'd you guys say? Halogen. Sorry. What's the halogen in the third period? Sorry. Bromine. Okay. Sorry, guys. Bromine. So write the complete electron configuration. What's on 3? I'm sorry, I don't have a periodic table in front of me. Chlorine? Fluorine, chlorine. Yeah, chlorine. Sorry, guys. I don't know if you noticed, but I literally brought absolutely nothing to class. To class? To SI. Oh my God. Okay, someone read me the electron configuration. Okay, there's an error on my key. I put 6 because I was thinking noble gas. So, just saying. If you look back on my answer key, there's an oops. Box in the valence electrons. What am I going to box in here? Yes. These are the valence electrons. These superscripts add up to 7, right? And the halogens have 7 valence electrons. Okay, write a complete set of quantum numbers for the last electron in the element above. What's our n quantum number? 3. Okay, I'm going to show you guys another way to write this because I feel like I should. What's our L quantum number? 1. What about our M sub L? 0. And this can be plus or minus -1/2. Because remember, p orbital, 3 orbitals, right? We have 5 in p, so we go 1, 2, 3, 4, 5. We ended at 0, it's 0. No, you're good. Okay, so the p quantum number, so this is how you got the 0. Sorry, I did not see the chat until just now. The L quantum number is assigned by orbital type. So we have s, p, d, and f orbitals. S is 0, p is 1, d is 2, f is 3. And that's it. Okay. So, which of the following is not a valid set of quantum numbers? Yes, C. And this goes back to 1p, which doesn't exist. I really tried to find like another one of her questions that was like, which isn't valid, and it's not 1p is the answer, but I couldn't find one, so. Okay, so we just finished quantum numbers. Let's jump into periodic trends. In general, as you go across the periodic table, as you go across a period in the periodic table from left to right, the atomic radius will increase or decrease. The electron affinity becomes increasingly or decreasingly negative, and the first ionization energy increases or decreases. Okay, we have an online answer. What about in person? Huh? B. Ionic radius will decrease, electron affinity will become more negative, and first ionization energy will increase. Yeah. I know I've said this before, but some of you guys only come to test preps, which is totally cool because that's what I did too. So no judgment. But basically, I told you guys to just remember this. These arrows are both increasing. On the worksheet she gave you or the note sheet she gave you, she goes back and forth between increasing and decreasing, and I don't like that. I'm keeping it simple. Each of these arrows means increasing. Going down is radii. This is atomic and ionic radii. Increase is going down. Everything else is going to increase going up. Everything else. Or I was looking back at my exam today, and like this exam that this was on, and I drew mine like this for radii and like this for everything else. And these mean the same thing. So yeah, that's how I learned it for my test, because learning all those other arrows and switching back and forth all the time, it just gets too confusing for me. And there's already a lot to remember for this test. Does anyone else get shocked? Like, no matter how many years you're alive, you just get shocked when it gets dark early again. It just feels really wrong. Like, it happens every single year. And every single year, I'm just, like, offended by it. Okay, elements from opposite sides of the periodic table tend to form covalent compounds. This one, it went on the back. I'm sorry. It went on another sheet. Okay, elements from opposite sides of the periodic table tend to form covalent compounds that are gaseous at room temperature, covalent compounds, homonuclear diatomic compounds, compounds that are gaseous at room temperature, or ionic compounds. We have an answer online. What about in person? Ionic compounds. On the left side of the periodic table, you have metals. On the right, you have nonmetals. You'll see she throws in some really like fancy terminology, things that she knows you don't know. Like, when are covalent compounds gaseous at room temperature? We haven't gotten to gases yet, right? So she'll sprinkle these things in, and it's stressful because you're like trying to reason it, and it's something that you don't know yet. Also, homonuclear diatomic compounds. That sounds like a really fancy way of saying the diatomic 7, right? Homo meaning same. Okay. In ionic bond formation, the lattice energy of ions. Hey. Come on now. Woo. In ionic bond formation, the lattice energy of ions blank as the magnitude of the ion charge is blank and the radii blank. So decrease, increase, 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 decrease, decrease. Okay, we have online answers. What about in person? E. If you'll recall, this was a question on your last quiz. And it was one that a lot of people really hated. It's one that I really hate. So my best recommendation is if this doesn't totally make sense for you, just like memorize it. Like, I know like I'm like an SIN tutor. I'm supposed to like encourage you to learn and not memorize, but sometimes you just have to memorize things. Okay. Blank have the lowest first ionization energy of the groups listed. Alkaline earth, alkali metals, halogens, transition elements, noble gases. I don't know, because like I pull these questions from my past exams and quizzes, and I took this class fall of 2018. So it's been a couple years, and the textbooks have changed. We use Pearson, you guys use OpenStack, so some things are different. Our tests are also different. For me, this test was chapters 8 through 10, meaning we had electron configuration, all that, in addition to stoichiometry and stuff, which really sucked, by the way. So, yeah, and like for the purpose of like integrity of grades and stuff, I'm not allowed to know what's on the upcoming exams or quizzes. I'm not allowed to know you guys' grade or even like your classification or anything like that. Okay, what about in person? What's your answers? B. And this goes back to ionization energy is one of our periodic trends, right? And it's not a radii, so it must increase going this way. So the lowest energy must be over here, right, where those alkali metals are. Okay. Atomic radius generally decreases as we move up or down. Decreases as we move up, decreases as we move right to left or left to right. Right to left. Sometimes I forget what's my right and what's my left. Because remember, I said to remember the increasing, so the decreasing must be the opposite of that, right? Yeah. I may have said right to left, and then I think I did say right to left. I said that, and then I answered differently. Yes, it's left to right. Sorry. The blank have the most negative electron affinities. Halogens, chalcogens, alkali metals, transition metals, alkali earth metals. Oh, this should be alkaline. No, this should be alkaline. Okay, we have an online answer. What about in person? Halogens, because electron affinity is another periodic trend, right? Do you see how just remembering those two arrows can answer so many questions? Okay, in the nitrite ion, both bonds are the same. One bond is a double bond and the other is a single bond. There are 20 valence electrons. Both bonds are double bonds, or both bonds are single bonds. This means you're going to have to draw out that Lewis structure, right? What's the formula for the nitrite ion? Because remember, it's an ion, it has a charge that's going to impact that Lewis structure, right? So what's that formula? Yes. Okay, I'll let you guys like draw that out. Okay, we have an online answer. Yes, B. There's one double bond and one single bond. So let's see, nitrogen has 5, oxygen has 6, there's 2, that's 12, and then we have 1. So there's 18 valence electrons total, so C is out. That's used up 4, so now we're down to 14. 6. That's the structure. Ideally, you would use pencil and erase those 2 electrons, but I didn't bring anything, so I only have a pen. Oh, there we go. That's the structure. Okay. I didn't put anything about formal charge on here, but I want to do this. I want you guys to calculate the formal charge of all the atoms on this molecule for me. What's the formula for formal charge? Yes. Yeah, you'll put a bracket around it and the charge up in the top corner so that you know it's an ion. Yes. The formula is going to be valence electrons, and by that I mean what you get off of that periodic table, minus lone electrons, minus bonds. No. 2 of those are correct, and 1 of them is not. Because think about it, a positive one and a negative one, they're going to equal out to a 0, right? But we have to end up with a -1 charge. So let's do this one. Oxygen has how many valence electrons? Yes. 6. How many lone electrons? 6. And 1 bond. So 6 minus 6 minus 1, -1. Nitrogen has 5 valence electrons, 2 non-bonding. So 5 minus 2 is 3, minus 1, 2, 3 bonds, that's 0. Oxygen has 6, minus 1, 2, 3, 4 non-bonding electrons is 2, minus 2 bonds, 0. Do you notice how all of these add up to equal our charge? That will always be the case. If you add up the formal charges you've just calculated and they don't equal the charge of the ion, something's wrong. Okay, which atom can accommodate an octet but doesn't necessarily have to? Hydrogen, nitrogen, carbon, oxygen, boron. Yes, E. The only other element here that's not going to have an octet is hydrogen, but it can't accommodate an octet, right? It can only ever have 2. Boron, so the 2 atoms, boron and beryllium, are satisfied with a sextet. Or or 6 electrons. We see this in boron plus a halogen, so boron trifluoride looks like this. The number one mistake students will make on a question like this is they'll try and put a double bond in here. Don't do that. Boron, beryllium, they're just weird. Yeah, they're just weird. But those are the only two you have to remember that don't form an octet. Besides hydrogen, but hydrogen is a little different because it can only ever have 2. So whereas boron and beryllium, if needed, they can take on 8 electrons. If that's what the molecule calls for, it can do that. But they can hang out at 6 and not have any issues. God, my fingers are freezing. Okay. To convert from one resonance structure to the other, to another, electrons and atoms can both be moved. Only atoms can be moved. Neither electrons nor atoms can be moved. Only electrons can be moved, or electrons must be added. Okay, we have an online answer. What about in person? In person. D. Only electrons can be moved, because what is a resonance structure? We're moving a double or a triple bond, right? Those bonds show us electrons. We're just moving electrons around. That's it. So of a carbon to, okay, this was wordy because on her question, she like had all the lines. I couldn't figure out how to get that triple bond. So a carbon to nitrogen single bond, a carbon to nitrogen double bond, or a carbon to nitrogen triple bond. The single bond is the weakest and longest, strongest and shortest, strongest and longest, intermediate in both strength and length, or weakest and shortest. And I'm putting this on here because I said something to a few people I tutored, and then I realized last night that I was wrong. So I need to correct myself. It's C. I'm sorry, you guys. I told a lot of you that triple bond was the strongest, and I lied. And I'm so sorry for that. So here's how I want you to think about it. Whenever, so, how do I want to go about this? So you have that single bond, right? I'm going to make this longer. Then you can have a double bond shorter. Oh, sorry. Then you can have a triple bond shortest, right? So it's kind of like you're dividing up that length, right? Right, like you're taking that bond, you're dividing up that length, you're making 2 bonds. And same with a third bond. Does that make sense? I want you to think about the strength in the same way. You're dividing up the strength each time you divide the length. How do you guys feel about that? Because I don't like it. Yes, single is the strongest. And I know this is right because I pulled it off of her exam, her old exam. So yeah. Yeah. Oh, what the hell? Oh my God. So yeah, I'll figure that one out for you. I'll send it out in the remind. Okay. On to stuff that I do know for sure. In the molecule below, which atom has the largest partial negative charge? Fluorine, carbon, iodine, chlorine, bromine. Okay, we have online answers. What about in person? A. It's fluorine. Why? It's the most electronegative element. It's the most electronegative out of the four surrounding it, meaning this is going to pull harder than these other ones. Then chlorine is the next. And each time that arrow just kind of decreases. This has the strongest pull, and we know that because of electronegativity. So if it's pulling the electrons closest to it, we're going to get a partial negative charge. If you're going into OChem, get really comfortable with this idea. It's big. This symbol, it's a lowercase delta. It just means partial. It's a partial negative charge. So technically, all of these have a partial negative charge, right? They're all pulling away from carbon. This one just pulls the furthest and the strongest. Does that make sense? Okay. A typical triple bond consists of 6 shared pairs of electrons, is longer than a single bond, consists of 1 sigma bond and 2 pi bonds, consists of 3 shared electrons, or consists of 2 sigma bonds and 1 pi bond. C. Okay, I see you, James. Don't worry. So funny. Okay, because think about, oh no, I don't want to show you guys that yet because we're going to do that. Okay, the hybridization of the terminal carbons in this molecule is, she'll give you something like this. She wants you to redraw the molecule. So basically what this is saying is we have a carbon double bonded to a carbon, double bonded to another carbon. On each of these terminal carbons, we have 2 hydrogens on them. That's all that's saying. So what's the hybridization of those? Notice how they're exactly the same, right? Those 2 terminal ones, they're just kind of flipped. It is B. So I'll show you guys how I figure this out. There's 2 ways. You can learn it off the Vesper sheet, but that's a lot. There's already a lot to remember off the Vesper sheet. So what I personally do, I'm going to recommend you erase this before you turn in your exam. So every time I show you guys a trick, someone gets points taken off for like writing it down. So write it down to do it, to figure it out, and then erase it, get rid of it. So we know that we have to have one, we can only have 1 S, we can only have 3 P, and we can only have 2 D, right? S, SP, SP2. Does that make sense? So we start off with S. I don't know if you can use Vesper sheet or not. That's definitely something I would email her about and ask, because she has not told me anything on that. So start off with S, can only have 1 S. I've used that, so now we have to start adding P, SP, and then SP2. So notice in SP2, this S, there's an understood 1 superscript right there, right? What's 1 plus 2? 3. How many regions of electron density are on this carbon? 3. 1, 2, 3. So make sure your superscripts add up to the number of regions of electron density. One thing I want you to notice off your Vesper sheet, this applies even to lone electron pairs. this has 6 regions of electron density, right? If you go on your VSEPR sheet, you look under octahedral electron domain geometry, it's going to say sp3d2. And that's just saying SP, SP2, SP3, SP3D, SP3D2. Those superscripts add up to 6. That happens. No, there will never just be, oh, well, if you have H2, then yeah. But honestly, don't worry about H2. You're not going to have to worry about H2. Ugh. So really, you would have to remember that these are the only hybridizations you can ever have. These are the only ones you'll ever have. So whenever you're given a molecule, like for this central carbon, how many regions of electron density are there? 2. We need our superscripts to add up to 2, and that only happens here in SP, right? Or you could do SP. It's SP. Same thing over here, SP, SP2. That's it. There's no, the way I'm explaining this to you, the way I'm showing you this trick, there's no like really sciencey explanation for it. Because I know she gave you guys a whole bunch of information over hybridization, and you just don't really need it to figure out the hybridization if you can do this. Yeah, of course. I mean, honestly, we're going to have time, so I'll do one. Let's do carbonate, because I've been working with that a ton. A hybridization is an overlap of orbitals. So here on this carbonate molecule, I didn't draw in the lone electron pairs, but that's fine. How many regions of electron density? 3. What do our superscripts have to add up to? 3. So we have S, we have SP, we have SP2. That's a hybridization. Yeah, this is chapter 8. You know what? I'm going to go back to question 26. Oops. And I'm just going to go ahead and go with you guys on weakest and longest, because it's more possible that she messed up grading my exam than she messed up on all of you guys' notes and quizzes and stuff. Yeah, so do that. I'm comfortable telling you guys that. Okay. Now we're going to MO. Molecular orbital theory correctly predicts paramagnetism of oxygen gas O2. This is because the energy of the pi 2p MOs is higher than that of the sigma 2p MOs. The O to O bond distance is relatively short. There are 2 unpaired electrons in the MO configuration of O2. There are more electrons in the bonding orbitals than in the anti-bonding orbitals, or the bond order in O2 can be shown to be equal to 2. And Madison, yes, weakest. Also, how do you guys feel about molecular orbital in general? No? Okay. Okay, we have one good. That's good. So someone take a shot in the darkness. You have a 20% chance of getting this right. What was that? Not D. It's C. It's C. Whenever you have unpaired electrons, you're going to have a paramagnetic molecule. If all of the electrons are bonded in that center part, that's going to be dimagnetic. Yes. I say yes. I don't know for sure that you'll have to, but I am saying it's very likely she'll give you a diagram and want you to fill it out. So that's what we're about to do. I have 3 ones that we're going to fill out and go over. Okay. The bond order of any molecule containing equal numbers of bonding and anti-bonding electrons is 0. Anti meaning like against, opposite. If they're equal, they're just going to cancel each other out. What's the formula for bond order? Yeah, I mean, those are the same thing. Bonding minus anti-bonding divided by 2. Or you can write it, bond order is equal to 1/2 bonding minus anti-bonding. These two mean the exact same thing, just different ways of writing them. I like this one most. I don't like multiplying by fractions, so. Okay, let's practice some molecular orbitals. So first we're going to do oxygen gas. Okay, so first I really want to sort of break down this diagram for you so that you know what the heck is going on here. So these 2 on the edges that go up, these are atomic orbitals. This middle one, this middle piece right here, is molecular orbital. This is what it's named after. So notice how our molecule, what's oxygen gas? O2. Our molecule is O2. It's made up of the 2 atoms of O and O, right? So another thing that I wanted to cover real quick. What does this asterisk mean? Anti-bonding. Above the center line, these are above the center is always going to be anti-bonding, below it is always going to be bonding. Same here. Okay? Next up, do you see this sigma and pi? Where have we seen sigma and pi before? What was that? When we're talking about like bonding and stuff, right? We can have 1 sigma bond, we can have 1 sigma bond, 1 pi, 1 sigma, 2 pi. This diagram will tell you if you know how to read it. And that's what we're gonna do. Yeah.
When you fill this in, do you have to fill in the sigma ones before you fill in the pi?
So that's a good question. So they asked, when you're filling this in, do you have to fill in sigma before pi? No. You're just gonna go from top to bottom to top. Okay, focus. Okay, how many electrons does oxygen have total? Not just valence, total. 8. Does everyone agree on that? It's just that atomic number, right? Do you remember when we did isotopes? It's just the atomic number. So we have 8. How many electrons can each orbital hold? 2. 1, 2, 3, 4. And remember, when we were filling orbitals before, we have to fill them all up once before we can fill them up doubly. And it's true here. So we have 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense? This is still oxygen. We're doing the exact same thing over here. And also, I want to say, I have never seen her do one of these where you're doing 2 different elements. I've never seen her do that. So what are we going to do in this middle part? We're summing it up. We're moving it all here. So how many electrons total are there in this 1s? 4. So like I said, we're going from bottom to top. 1, 2, 3, 4. Same thing here, right? We have 4. 1, 2, 3, 4. How many do we have in this top one? Yeah, you're right. 8. So like I said, we're just going bottom to top, left to right like normal. 1, 2, 3, 4, 5, 6, 7, 8. So remember, remember this question, number 30? It's paramagnetic because there are 2 unpaired electrons. You see those 2 unpaired electrons? If they're unpaired electrons, it is paramagnetic. Okay. So bond order is bonding minus anti-bonding, right? And we said before, anti-bonding is these ones with asterisks, anything above that center line. So how many bonding electrons are there in the molecular orbital? There is 10. How many anti-bonding are there? 6. Divided by 2, that's going to give us 2, right? What's the Lewis structure for oxygen? It looks like this, right? We have 2 bonds. Does that make sense? Do you guys feel more comfy with molecular orbital? So 10, I got that from the bonding. So let me zoom in real quick.
So we won't have to draw this out, right?
No, you won't have to draw this out. She'll give you the diagram, you just have to fill it in. So the ones without asterisks are our bonding. So we have 1, 2, 3, 4. Come up here, 5, 6, 7, 8, 9, 10. Does that make sense? I don't know what she'll have you do for online. I don't actually. If you wanted, I would definitely email her about that and ask if you're able to print off one of your own to fill out. Yeah, that's what I would do. Okay. The number 6. So the 6 came from our anti-bonding, which is these with asterisks. So we have 1, 2, 3, 4, 5, 6. That's where that comes from. Wherever you see that asterisk, that's an anti-bonding. Okay, I really hate that I put oxygen first because oxygen is probably the most like weirdest to explain with this. But I'm gonna do my best. If it doesn't make sense, just hold on. It'll make more sense when we do nitrogen. So notice how I said you can figure out the pi bonds and sigma bonds from this. You have 2 pi anti-bonding electrons, right? And that's going to cancel out 2 bonding pi electrons. Anti and bonding cancel each other out. We have 2 here. It cancels out to here. Don't draw this. Don't draw this. I'm just showing you something. So when we do that cancel out, we're left with 1 sigma bond and 1 pi bond, right? Here we have 1 sigma bond and 1 pi bond, right? That's how this molecular orbital diagram works. Okay, let's try another. Let's do nitrogen. I like nitrogen a lot. How many electrons does nitrogen have total? 7? Okay, thanks. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And now we're just going to mush them together. We have 4 here. 1, 2, 3, 4. Same here. 1, 2, 3, 4. Here we have 6 total, right? 3 on each side. 1, 2, 3, 4, 5, 6. How many bonding electrons do we have? How many? 10. That's these at the bottom of the halfway mark in each of these. How many anti-bonding? 4. Divided by 2, that's going to give us 3. Remember, nitrogen looks like this. Our bond order is 3. We have 3 bonds. That's what the bond order tells you. So looking back up here at this last one, what part of it? So I can't like refill in the diagram because I wrote in pen. But basically, nitrogen has 7 electrons, and you get that from the periodic table, that atomic number. So you draw in 7 going up, because basically, and I always label mine N, N, and N2 is the molecule, so that way I with 7, you go all the way up until you fill in 7, and same on this side because it's also nitrogen. And then you're just going to add these together, fill them up. So 2 plus 2 is 4. 1, 2, 3, 4. Same thing here. 2 plus 2 is 4. 1, 2, 3, 4. Here you have 1, 2, 3 plus 1, 2, 3. So you fill up 1, 2, 3, 4, 5, 6. Then when you do that bond order, that's the formula we went over, where you have bonding minus anti-bonding divided by 2. So we get the 10 from looking at our bonding, which are these without the asterisk. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 arrows, 10 electrons. Now we move to our anti-bonding. So we have 1, 2, 3, 4. These are the ones with the asterisks. So 10 minus 4 divided by 2 is 3. And that tells you how many bonds are between those 2 atoms. So notice here in this 2p, we have 2 pi orbitals and 1 sigma orbital filled up, right? Is there anything canceling either of these out? No. And in this nitrogen, we have 1 sigma, 2 pi. That's how that works. Okay, I just have one last one for you. And I want you guys to do it on your own, and I'll follow up behind you. just so you can make sure that you do know what you're doing. You're not just following me. Yeah. Yes. That N2 is dimagnetic because there's no unpaired electrons. Thank you. I meant to ask that and then I did not. So fluorine gas, we have F, F, F2. So go ahead and do that one and I'll follow up behind you. So it's dimagnetic because if you look back, there are no unpaired electrons up here, right? Whereas with oxygen, we had some unpaired ones. So whenever there's unpaired ones, it's it's paramagnetic. Whenever they're all paired up, it's dimagnetic. Um, did y'all get this? Okay. How many bonding electrons are there? There's 10. How many anti-bonding? 8 divided by 2 gives us 1. The Lewis structure, single bond. And then if you go up and you look here, 2 anti-pi bonds cancel out 2 bonding pi bonds. And then you're left with just this sigma. So up at the top, we have 2, 4, 5 in each. So when you add it up, you get 10. So you need to end up with 10 electrons in this middle part. So 2, 4, 6, 8, 10. Is this dimagnetic or paramagnetic? Dimagnetic. Oops. That's all I have for you guys. If you have questions, you can come ask me. That's all I have. Uh-huh.
So we didn't have like the people chart going on, and we only had the signal one as like it was all just written out like that. Cloud one is signal one is. How do you do it like that?
What do you mean?
Because we don't have the diagram, just have the letters. So it just be like the signal one as, the signal asterisk one as, and then the signal two as.
Yeah. Honestly, don't worry about the 1s, 2s, 2p. You don't have to worry about that. So the dimagnetic, it's dimagnetic when you look at the molecular part of it. So, wrong way. So remember, this part is the molecular part. So whenever all of your electrons in it have a pair, it's dimagnetic. Unlike oxygen, Oxygen, we did it, and we had these 2 unpaired electrons up here. If there's any unpaired electrons in this middle section, it's paramagnetic. The 5 electrons in the 2p on the fluorine came from, oh shoot. Fluorine has 9 electrons total. So this fits 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Bond order, you're just going to, where is it? You're just going to follow this formula every single time. It's going to get you the right answer every single time. You can use either of these. They're the exact same formula. They're just written a bit differently. It just depends on what you prefer. And the bond order is how many bonds are in between those 2 atoms. For the zinc thing, that's just her following the electron configuration. And we did do zinc. Question number, we did do zinc, right? Number 7. This is all she did. She just did the electron configuration, saw that it's 3d10, it ends right there, and that's how she knew it was zinc.
She said that on the test, you could use the periodic table and the flow chart, but you have to memorize the front of the Vesper sheet.
Okay. So Adam said that on the test, you can use the flow chart and the periodic table, but you have to know the Vesper sheet. I didn't put geometry on this because I beat geometry to death in some of my other worksheets, so you can go find those on my website. I also have a Quizlet set on my website over predicting geometries. So if you're still struggling with that, go ahead and do that. I think the flow chart is the one on the back of on the back of your periodic table. Yeah, if she's asking, there's 2 ways that this can go. She'll either give you an element and she'll say, hey, find me the electron configuration for this, or she'll give you an electron configuration and say, hey, what element is this? Okay, are there any more questions on Zoom? Okay, I'll go ahead and end the meeting. Good luck on your exam and have a good night.